So as Anton is bringing up his slides, I'll give him a little bit of a more introduction. So Dr. Anton Ermakov is one of our co-leads of this study. He is an expert in planetary geophysics and determining the interior structures of solid bodies across the solar system with a variety of geophysical and geodetic data sets, including gravity and topography. He got his PhD at MIT in 2016 and is currently a postdoctoral researcher at the University of California, Berkeley. And as I said before, he'll give us sort of the primer to set the stage for geodesy across the solar system, starting with the Earth and Moon. So go ahead, Anton.
Good. Okay. Thank you, James, for this introduction. Good morning, everybody. Good afternoon. Thank you for coming to the short course. So I'll be talking about what geodetic data gave us in the Earth-Moon system before we continue our journey to the other planets of the solar system. And I'll be talking about planetary geodesy. So first, maybe we should define what planetary geodesy is. So you can think about it in maybe two ways. It's a measurement science about how to do measurements on the surfaces of planets. And it's also a branch of geophysics. And it is a study of planetary shape, the orientation of the planet, its rotation state, and gravity field. Historically, by geodetic data, people meant measurements of distances and angles on the surface of the Earth. And now we have much wider variety of data sets. We have radio and laser ranging to planets, moons, and spacecraft. We have measurements of the gravity field, both from spacecraft and on the surfaces of planets. We have measurements of the changes in the gravity field, which is called gradiometry. We can do stereo imaging of planets, basically looking at the surfaces and how these surfaces deform with time. And there, of course, there are many other types of data sets which we use in planetary geodesy. Why do we do all this? Well, this kind of data allows us to study planetary dynamics, planetary interior. It also has very practical applications, such as establishment of reference frames and spacecraft navigation, and also just navigation on the surface of planets. Planetary geodesy covers a range of spatial scales and temporal scales, ranging from kilometers to the global scale, and ranging from seconds to millions of years in terms of the temporal time scale. And this table just shows example geophysical signals that geodetic data allows us to study. So, of course, we don't have time to go in detail about all of this. So I basically chose 5 exemplary problems which geodetic data helped us with. So, and this is a list of 5 problems I'm going to cover in this presentation, starting from very basic understanding of the shape of the Earth and how geodesy allows us to connect it to the internal state of the Earth, then isostasy and flexure of the Earth's lithosphere, then also how geodesy helped us to accept and measure plate tectonics on the Earth, and finally we're going to discuss orbit-based measurements and how geodetic data, measurements of the gravity field, provided constraints on the climate change on the Earth. And the last topic would be, we'll go to the moon and look at the question of formation of lunar mascon basins and how the gravity data helped us understand the mechanism of lunar mascon formation. But first, let me give you some math background, and it won't be hard, but it will be useful for the following talks today as well. So mostly in this lecture series, we will be talking about planetary shape and gravity measurements. And they are commonly represented using spherical harmonic series, which is a set of orthogonal functions on a sphere, and it's an analog of Fourier series. And this animation shows individual spherical harmonic functions of various degree and order, and you can take these functions, you can apply them, you can multiply them by the appropriate coefficients. So in this case, it would be C for gravity and A for the shape. You can sum them all together and you can get a shape model or a gravity model of a particular body. So for example, this animation shows how I get, as I keep more and more terms in spherical harmonic series, how I get higher and higher resolution of the shape model of asteroid Vesta. In the solar system, we measured shapes and the gravity fields of multiple bodies, such as planets, the moons, asteroids, and even comets. And their spherical harmonic expansions range up to degree 1000, which is in the case for the moon. And I should remind you that the degree is inversely proportional to the wavelengths of a particular signal. So we have degree of maybe about 1000 for the moon, order of 100-ish for the terrestrial planets. And in the outer solar system, we don't have high resolution gravity or shape data with spherical harmonic expansions reaching maybe order of 10. But in the first part of the talk, I will be talking only about degree 2 shape of the Earth, basically the very long wavelengths structure in the Earth shape. And the question of the Earth shape is perhaps the first geophysical insight geodetic data gave us in the scientific era. It was a big debate in the 18th century. What is the shape of the Earth? Basically, there were two camps. So Newton predicted that the Earth would be like this orange. It would be like an oblate ellipsoid with the equatorial axis longer than the polar axis. Whereas Cassini, famous astronomer, used geodetic measurements and concluded the opposite, that the Earth would be a prolate ellipsoid with the polar axis longer than the ellipsoid, longer than the equatorial axis. What Cassini did, he built a geodetic triangulation network, basically a long sequence of triangles going from north of France to south of France. And he concluded that the shape, basically the curvature of the Earth's shape, is larger as you move toward the pole compared to the equatorial regions. And he concluded this just based from this triangulation network, which covers relatively small region on Earth. Newton was genius. He didn't even need data. So Newton's reasoning was based on physics. So he assumed that the Earth shape is an ellipsoid, and he used a simple equilibrium argument. He said, what if you drill two canals to the center of the Earth, one at the equator and one at the pole, and fill these canals with water? The weight of these water columns should be the same if the system is in equilibrium. And Newton was able to connect the difference between the equatorial axis A and polar axis C to the ratio of centrifugal acceleration at the equator to the mean gravity field over the surface. Moreover, Newton actually predicted numerical value for the Earth flattening factor. According to his predictions, it should be 1/230. In modern terms, Newton used the concept of hydrostatic equilibrium, a state in which the gravity force is balanced by the sum of pressure gradient and centrifugal force. In hydrostatic equilibrium, the surfaces of constant density and constant pressure would coincide, and there would be no shear stresses in the body. So the French Academy of Sciences decided to resolve this debate and sent two expeditions, one to South America, modern-day Ecuador, which was led by Charles de la Condamine, and the other expedition to modern-day Finland, the Lapland region near the Arctic Circle, and this expedition was led by Pierre Bouguer. And combined triangulation measurements in Lapland, in South America, and France showed that the Earth was oblate. And Euler was able to use this data and actually computed the value of ablateness of 1/229, which was remarkably close to Newton's prediction. So Newton was right. Well, he was kind of right. The modern value is actually 1/297. And Newton's prediction was 1/230. So what would cause this difference? Was Newton wrong? Well, not really. Newton made one assumption. This assumption was basically that the Earth is homogeneous in density. So in reality, Earth's density is not homogeneous. Earth has higher density at the center. Most notably, Earth has the core, higher density core. And the gravity field would be stronger on average within the body with a higher density center. And gravity is what keeps the body spherical. Thus, for higher density near the center, gravity would be stronger in the interior, keeping the body more spherical. And this figure shows just the gravity profiles for a simple two-layer model of the Earth. And the colors represent the density of the outer layer. So this would be a uniform model. This would be a differentiated model with a higher density core. And this green curve is actually shows the modern understanding of the Earth's interior. So just for fun, I made this animation illustrating the effect of rotation on the shape of the Earth. So let's play it. I considered also two cases here. The top one where density is nearly uniform, and the bottom one is where you have a higher density core. And you can see as I spin up the body, as I decrease the rotation rate, decrease rotation period, you notice more and more the difference in the ablateness of the two bodies. And you can see it more clearly for other bodies in the solar system, such as fastly spinning asteroids, Vesta and Ceres, where you can just visually observe this difference between the basically these circles and the shape of the bodies. Okay, so here's a little bonus. I compiled a list of references which I find useful for this particular topic, and I will have these lists of references for other topics as well. So maybe you can just take a screenshot. Also, this presentation will be shared later, so you'll be able to just go here and find these references. Okay, let's move on to the second topic, which is the isostasy. On the South expedition, there was another key figure. His name was Pierre Bouguer, and he was a pioneer of gravity measurements on the Earth. So while in South America, during his spare time, Bouguer set out to measure the gravitational attraction of the mountains, the Andes. Specifically, he wanted to measure how the local gravity direction would deviate due to the mass of the mountains. And he did these measurements, and he indeed found this deviation, but it was much less than predicted. And later, same result, but with higher accuracy, was acquired by the geodetic survey campaign in India in the Himalayas. Basically, the mountains weren't as massive as expected. So where is the missing mass? In 1855, Airy, just here, and Pratt independently proposed two rather similar hypotheses to explain this phenomenon, which are now known as Airy and Pratt models of isostasy. The two models call to mind the Archimedes principle, which says that a floating body displaces its own weight of fluid in which it is immersed. In an isostatic model, the Earth crust behaves as if it consists of blocks of floating blocks on the underlying mantle, and Airy varied the thickness of the crust while keeping the crustal density constant, while Pratt varied the crustal density to maintain the total mass of the crustal columns. Isostasy effectively minimizes pressure gradients at depth, thus minimizes lateral flow below the depth of compensation. And a good analogy for the area isostasy is just a floating iceberg. In reality, the picture, of course, is more complicated. The crust is not just disconnected floating blocks. The outer layer of the Earth can transmit stresses over large distances, and this mountain effectively acts as a load which can bend the elastic lithosphere. And the weight of this load could be supported at least partially by elastic stresses within the lithosphere. The amount of bending depends on the effective rigidity of the plate. If the plate is thick, let's say compared to the size of the load, it doesn't bend much. So infinite thickness elastic lithosphere would represent an uncompensated limit, basically no isostatic compensation. Whereas if lithosphere is thin, it is easy to bend, and in the limit of 0 lithospheric thickness, it corresponds to an isostatic model. Let me also introduce you to some gravity-dated terminology and gravity anomalies for different crustal structure and members. So the general formula for a gravity anomaly is that it is equal to observed gravity minus gravity of some model. And in the case of the so-called free air gravity anomaly, this model is simply a model of the planet in hydrostatic equilibrium, as if there is no topographic load, some non-hydrostatic, there's no non-hydrostatic topography. The Bouguer anomaly is defined also as a difference between observed gravity and gravity of the actual Earth shape, meaning taking into account the gravitational attraction of the topographic load. So in this picture, you can see that, say, I put a mountain here, and the free air anomaly would be positive, whereas the Bouguer anomaly would be 0 because I subtracted the gravitational effect of this mountain. And here's the case of isostatically compensated topography, which again can be thought of as an iceberg where the weight of the weight of the top of the iceberg is compensated by the displaced water, which is displaced by the bottom part of the iceberg. So in this case, the Bouguer anomaly would be negative due to the negative contribution of this negative density anomaly, which corresponds to the crustal root. And the free air anomaly would be mildly positive due to the fact that the mountain with its positive gravity contribution is at the surface, while the negative contribution of the crustal root is attenuated due to its depth. Sometimes you can also define so-called isostatic gravity anomaly. I think we're not going to discuss it in this lecture series, which is basically defined as the difference between observed gravity and gravity created by isostatic structure. So this is the gravity Bouguer anomaly map of the Earth, and you can see that essentially over all major mountain ranges you have negative gravity anomalies, indicating isostatic compensation. And this is another way of looking at the Earth gravity. It's radially exaggerated equipotential surface, also known as geoid. So here, red areas correspond to mass excess and blue areas correspond to mass deficit. Notice that red and blue colors, they don't correspond to, let's say, oceans versus continents, which attests to global compensation, global isostatic compensation. Instead, low wavelength geoid anomalies are related to the density anomalies resulting from and driving the convection in the Earth mantle. And here's again a list of useful references for isostasy and flexure. Okay. So I mentioned the convection in the Earth mantle, and let's probably go to the next topic here, specifically plate tectonics. So the concept of plate tectonics has been around for many decades, since the beginning of the 20th century. but originally it met a lot of resistance in the geoscience community. The basic idea is that lithospheric plates represent strong, nearly rigid outer layer of the Earth, which is moving over a weaker layer of asthenosphere. Lithospheric plates are effectively a thermal boundary layer of a convective system. And this schematic shows a cross-section in which the crust is being formed at the mid-ocean ridge and gets destroyed, sinking into the mantle at the subduction zone. The magnetic data over the mid-ocean ridges were particularly important for understanding plate tectonics. And this picture shows bathymetry, so topography of the ocean floor, centered at the mid-oceanic ridge in Atlantic Ocean on the left, and on the right shows magnetic anomalies that form this pattern of stripes, which is parallel to the ridge. The black and white colors represent alternating sense of polarity of the Earth's magnetic field recorded by the magnetized crust newly formed at the ridge. Correlation of these magnetic anomalies with the paleomagnetic data of the Earth's magnetic field reversals allowed estimating the spreading rate along the mid-oceanic ridge. So this was done probably in the 50s and in the 60s, and in the 70s and 80s, advances of the space geodesy techniques allowed to catch plate tectonics in action. Several techniques were of key importance. First, very long baseline interferometry, or VLBI, in which quasars are used as radio signal sources and terrestrial radio telescopes as receivers. The change in the distance between the two telescopes, which makes a baseline, can be determined to a centimeter accuracy over a period of years to decades. Second technique was called satellite laser ranging, SLR, in which the motion of spacecraft is tracked with a laser range measurement, which also allows calculating the baseline between the ground stations. And this is a figure from a rather old paper, which shows plate velocities in the Pacific Ocean. And this figure compares the predictions of plate velocities from geologic data on the x-axis to the geodetic data on the y-axis. And you can see that geodetic measurements revealed that the plate tectonic motions measured over time scales of decades match to a high level of correlation with the plate velocities inferred from geologic records such as magnetic stripes. Later, global positioning system made surface motion studies much more accessible. In GPS, the position of a receiver on the surface of the Earth is determined by simultaneous distance measurement to multiple satellites, multiple GPS satellites, whose orbits are determined by a variety of reference stations on the Earth. This figure shows the GPS-based solution for plate motion. So in summary, while the details of plate tectonics are being worked out right now, space geodesy has proven to be an invaluable data set for assessing the Earth tectonism. And again, this is a list of references which I found useful on this particular topic. Also, you can find some space geodetic data on the NASA Space Geodesy archive. Basically, you can look for references for VLBI, SLR, and GPS data there. Okay, now on to the orbit-based Earth gravity field measurements. Operating from 2002 to 2017, the GRACE mission opened up geodetic data for much wider geoscience community, as it allowed to quantify large-scale mass motion in the Earth system. The GRACE mission consisted of 2 satellites, and the primary measurement of the GRACE spacecraft was the distance between the 2 spacecraft. And this distance changes as the spacecraft fly over mass anomalies, allowing to reconstruct the gravity field. The advantage of the GRACE mission of this inter-satellite tracking concept is the locality of the distance measurement. Unlike the LBI, SLR, or GPS, the signal has to propagate a relatively small distance between the two spacecraft. So there will be no atmosphere or any type of ionized media in the way of propagating electromagnetic wave. And the position of the spacecraft is determined by the GPS. And there are also accelerometers on board of the two spacecraft to take into account the non-gravitational acceleration, such as due to the drag by the atmosphere. This animation shows reconstructed changes in the Earth gravity field. And red colors here mean stronger gravity, blue color means here weaker gravity. So you can notice two main signals here. So first, you can see very clearly a seasonal hydrological cycle, most notably in the Amazon basin and in the equatorial Africa. So you can see red, blue, basically alternating colors season after season. And secondly, you can see a trend in gravity over the massive ice sheets in the Greenland and Antarctica. And this animation shows how the mean value of the gravity changes over Greenland during the Grace mission time span. And it is shown here in rather strange units. The gravity change is recalibrated and presented in terms of the equivalent water layer thickness. The background graph here shows the integrated mass loss over Greenland. And there's the same animation for Antarctica. So basically, Grace data allowed to quantify the mass loss due to the climate change, and even allowed to detect the acceleration of the mass loss. You can see it getting redder and redder here, and in this image, red colors mean weaker gravity. Okay, and here's again a set of useful links for working with the Earth shape and gravity data. Okay, our last topic is about the moon. So the first mission to measure the gravity field of the moon was the Soviet Lunar 10 mission in 1966. So one could say marking the start of the planetary geodesy field. So this mission measured the spherical harmonic degree 3 of the moon. It detected that the moon gravitational figure is elongated along the direction toward the Earth. And this elongation basically provides a handle for tidal torque to keep the moon tidally locked. And you'll hear about tidal locking and the tidal torque, I guess, in the last talk today. 2 years later, the US Lunar Orbiter mission detected large unexpected accelerations acting on the spacecraft. These accelerations were so large that they presented a challenge to maintain stable spacecraft orbit. And this figure here also shows a gravity map of the moon. And it's a bit hard to see because it shows in digits the values of the surface gravity anomalies. But if I zoom in, you can see that over the Mare Imbrium, which is right here, and Mare Serenitatis, the authors actually ran out of digits and had to show strong positive gravity anomalies in letters. These strong positive gravity anomalies were dubbed mass concentrations or mascons, and their origin remained a mystery until the Grail mission, which was a dedicated mission to map lunar gravity field in ultra-high resolution. Like Grail consists of 2 spacecraft with the inter-satellite distance measurement. You don't have GPS around the moon, so you have to also track the spacecraft from the Earth to determine their orbit. to fully exploit the high resolution Grail gravity data, we also need to know lunar topography, for which the primary asset is the laser altimeter instrument called LOLA on board of the LRO mission. This animation shows the topography of the moon from the LOLA instrument, and the lunar gravity specifically shows the free air gravity anomaly. Just you can see in this right image here, you can clearly see the effect of topography on the gravity. So for example, all these blue circles are craters, so depressions. And you can also see that many large depressions on the moon correspond to positive gravity anomalies. Okay, this map shows the Bouguer anomaly from the Grail mission. And you can see that once you have accounted for the gravitational effect of topography, the map is much smoother. It's basically dominated by the yellow color, which is the anomaly equal to 0. Don't really see craters here, but instead you still see these very strong positive anomalies, which are associated nearly with every lunar basin. So how do these mascons form? Well, maybe their formation is a direct outcome of impact process. Let's say if the moon gets hit by an asteroid, it results in a crater, and maybe the impact was so strong that it affects the crust-mantle interface in such way that it results in an uplift of the crust-mantle interface, which can create positive gravity anomaly. So how much uplift is needed? Well, we can actually compute it from the observed gravity, assuming some density for the crust and the mantle. And we would conclude that such uplift would need to exceed the expectation from a simple isostatic balance model. So we can call it a super isostatic uplift. And super isostatic uplifts are a problem. Why are they a problem? Well, because basically it's very hard to maintain a super isostatic uplift. This animation shows the simulation of impact formation of a typical lunar mascon basin using shock physics code called ISAIL. And actually, let me play this animation. So you can see that as the transient cavity collapses, the crustal and mantle material are being sheared at such high rate, and let me play it again, that they behave essentially as a fluid, not being able to transmit shear stress. Thus, you end up with effectively isostatically compensated basin, which is inconsistent with the observations of strong positive gravity anomaly. So as I said, these gravity anomaly patterns were mapped in great detail by Grail mission, and in 2013, a group led by Jamie Losh proposed the following mechanism for mascon formation. They used a two-step approach in which the impact formation is modeled with a shock physics code, and this takes hours in physical time, this part of the simulation. And viscoelastic relaxation was computed coupled with a thermal evolution using a finite element code. And this part of the simulation takes millions or tens of millions of years. And the outcome would be to predict the topography, crust-mantle boundary, and gravity anomaly to be matched with the observations. So they found that the mascon gravity anomaly pattern results from impact basin excavation and collapse of the transient cavity, which is followed by isostatic adjustment of the basin. The formation of the lithospheric bridge. Okay, so after the lithosphere cools, the buoyancy force acts on the crustal, on the annulus of thick crust, which acts essentially as the lifesaver. And this buoyancy force can be transmitted to the inner part of the basin, providing uplift required to explain the observed gravity anomaly. The formation of this lithospheric bridge critically depends on the thermal structure of the crust. In summary, the Grail mission provided ultra-high resolution gravity data of the moon, which sparked interest in lunar geophysics and brought the right people together to solve this long-standing problem. And again, here are references which I find useful for modeling of lunar and planetary gravity. And this is my summary slide. So in the Earth, on the Earth, geodetic data were used to determine the shape of the Earth, which led to understanding that the Earth is differentiated. Analysis of geodetic data coupled with the gravity model led to understanding that the Earth's crust globally is in a state of isostasy. Space geodetic measurements revolutionized plate tectonic studies, confirming that current instantaneous plate motions agree with plate motions inferred from geologic data. Geodetic data from GRACE and from the current GRACE follow-on mission continue to quantify the effect of global warming on the ice sheet loss. And high-resolution lunar gravity data from the Grail mission answered long-standing question on the origin of lunar mascons. And with that, I conclude my talk and happy to answer any questions you have. Thank you.